Let us look at the solution of the second order linear differential equation with constant coefficients, which is also homogeneous. So the equation has the form a1d plus a0 acting on x equal to 0. I have already introduced the notation d for the derivative as an operator, and I have gone one step further here. Instead of writing the differential equation as, let's say, d square x by dt square, as we call it, plus a1 dx by dt plus a0 x equal to 0, where x is the unknown function of time which is to be determined, the right hand side is 0, so the equation is called homogeneous. So instead of using this more familiar d by dt or d square by dt square notation, I am using capital D to denote the derivative operator, so that dx dt will be replaced by d acting on x. It's just the derivative operation taking place on x. And similarly, d square x by dt square, which is d by dt of dx by dt, therefore becomes d acting on dx, and for short or for brevity's sake we write this as d square x, and I am reading it as d square x, but what it really means is d operated two times, d acting on x and d acting again on the result, which is dx. So with this then we have d square x dt square, so I can write d square x plus a1 dx dt, so I can write it as a1 dx plus a0 x equals the 0 function. The 0 on the right hand side is not the number 0, but it is the function 0. The function is 0 for all time t. On the left hand side also we have functions. X is the unknown function. For us it's a signal, so it's a function of time, something that changes with time perhaps. So all the left hand side quantities or expressions are functions. a0x is a0 times the function x, a1 dx is a1 times the function dx, and d square x is the second derivative of x, that is d acting two times consecutively on the function x. So that is what we have on the left hand side. Now instead of writing the three separate terms, I have written them in the form with which I started, namely I have written them as d square plus a1d plus a0 and put that in brackets and x equal to 0. And now we look upon this d square plus a1d plus a0 as a more complex operator. That is, just as the symbol d denotes an operation of derivative taking place on the function x to produce the function derivative of x, similarly this d square plus a1d plus a0 is an operation taking place on x, the function x, and the definition is simply this: operation acting on x by definition is simply the sum d square x plus a1 dx plus a0x. Such an operator is called a polynomial differential operator. For an obvious reason, it's a differential operator because the derivative occurs as a part of it, derivative two times, that is twice in succession, d square and perhaps d cube and so on, and it's called a polynomial differential operator because it looks like a polynomial in d. We are more used to polynomials in perhaps x and y or t, but here is a polynomial in this operator d. It looks like a polynomial, d square plus a1d plus a0. For example, in a particular numerical case it may be d square plus say 5d plus 6. This is a polynomial differential operator, and one can talk about the degree of the polynomial differential operator just as one talks about the degree of a polynomial, and the degree of the polynomial operator is 2 in this case. And we also talk about power of d, that is how many times at the most d acts. In this case d acts 2 times, so we say that the power of d is d square is the power of 2, and that is the highest power of 2 in this expression. Therefore the degree of the polynomial differential operator is 2. If you did not know that d was an operator, but you just thought that it was a symbol for a variable as in algebra, then you would have said that this is a polynomial of degree 2. But here for us d is the polynomial the differential operator, so what we have is a polynomial differential operator of degree 2. When talking about the differential equation, one talks sometimes about the order of the differential equation rather than degree, and one says therefore that the differential equation d square x plus a1 dx dt plus a0 x equal to 0 is the differential equation of the second order. So instead of talking about first order differential equation, then one talks about second order, third order, and so on. One could equally well call it the first degree or second degree differential equation, and so on. In fact, since we are calling the with respect to the polynomial, we are using the word degree. With respect to the differential equation also, we could use the same word degree, but some books do use the word order. All right. So we have this second order homogeneous linear differential equation with constant coefficients, and we are trying to find out what are all the solutions of it, because it may have more than one solution. Earlier we saw the first order differential equation, and then we saw that also the homogeneous equation had not one but infinitely many solutions, just the differential equation by itself, and therefore you needed something more, namely what is called an initial condition, to determine the solution uniquely. To repeat very quickly, the differential equation d plus a x equal to 0 has the solution x of t, that is the function x whose value at any time t is given by any number that you like k multiplied by exponential of minus at. This was the solution or the set of all solutions of the differential equation first order or first degree differential equation d plus a x equal to 0. Here k can be any number whatsoever, so for each value of k we get one solution, and therefore we get infinitely many solutions, or the set of solutions, which can be written as follows. The two braces, the curly brackets at the end, are supposed to stand for the set of all k exponential e raised to minus at for all possible values of k, that is k any real number 1, 2, minus 50, 10,000, what have you, multiplied by exponential minus at. Each one of them is a solution of the differential equation. Now we have a differential equation of degree 2. So what do we do about it? How do we find its set of all solutions? Now I told you that the way in which one solved this differential equation d plus a x equal to 0 by actually remembering the exponential function and remembering some simple properties of the exponential function. That was one way of doing it. That is, suppose you were presented the definition of the exponential function, and that can be done in several ways. For example, one can define it in the form of an infinite sequence and so on, which you may recall from your calculus courses. So when you have the definition of the exponential function, that is, it is this function, then one can examine its properties. For example, one can study, I showed you the graphs of the exponential function, or the graph of the exponential function, which is a very important graph, that it is never equal to 0, at t equal to 0 it is 1, etc. One can study some more properties of the function. For example, what about its derivative? And this is one of the basic exercises or results in calculus, that if I look at the function e raised to t, then its derivative is simply e raised to t itself. That is, differentiating does not change the function. E raised to t after differentiation gives you e raised to t only. The function e raised to t is unchanged by differentiation operation. However, if I have e raised to at, that is, the exponent is now at, exponent of e is at, then the derivative of that is no longer e raised to at, but what is it? A times e raised to at. So the d operation does not change the function e raised to t, but the d operation changes the function e raised to at, and what it does to the function is simply multiplies it by the number a. Similarly, if I have e raised to minus 3t, the derivative operator on that would multiply it by minus 3. So the derivative of that is minus 3 into e raised to minus 3t. This is the property of the exponential function which we use to see that d plus a x equal to 0 has xt equal to k exponential of minus at, or rewriting it also as k e raised to minus at for a solution, because simply apply the derivative operator to k e raised to minus at. So d acting on k e raised to minus at is equal to what function? First of all, the derivative operator has the property that if you have a multiple of a function and take the derivative of that product, that multiple, then it is the multiple of the derivative of the original function. Therefore, d acting on k times e to the minus at is simply k multiplying d acting on e raised to minus at. But d acting on e raised to minus at is in turn minus a times e raised to minus at. So, the derivative of k times e raised to minus at is minus ka e raised to minus at, and therefore, we can simply now verify that k e raised to minus at is a solution of dx plus ax equal to 0, because if x is k e raised to minus at, then dx is this. So, I have minus ka e raised to minus at, that is my dx if x is e raised to k e raised to minus at, plus a times x, but x is k e raised to minus at, this is ax, and a simple addition shows that the result is 0. So, the exponential function or any multiple of it, any arbitrary multiple of it, is a solution of the first order or first degree linear differential homogeneous differential equation with constant coefficients. So, this is one way of obtaining the solution, by simply knowing that the exponential function has such and such property. In advanced courses in mathematics, of course, one can approach the matter a little differently, because there you not only talk about linear differential equations with constant coefficients, homogeneous or non-homogeneous, but even non-linear differential equations, and then ask questions, does it have any solution, how shall we find the solution, and so on. And so, quite different technique has to be used for investigating that problem. For our purposes, we know the exponential function already, we have to remember its property with respect to differentiation, and then we have a ready-made solution. How to evaluate the exponential function is a different matter. Of course, your calculators do provide the exponential as one of the functions that are available, but you will recall that the exponential function is given either by an infinite series or by the limit of a sequence. Just to remind you, e raised to at, what is the infinite series for it? Now, this is again something every electrical engineer must know by heart and must not forget it, as long as he can afford to remain an electrical engineer. What is the exponential, the so called power series expansion for e raised to t, which is also the Maclaurin series for e raised to t. It starts off at 1 plus t divided by, for the sake of generality I am writing t divided by 1 factorial, t square divided by 2 factorial, plus t cube divided by 3 factorial, plus, and so on, because the thing continues without any end. This is the infinite series expansion for e raised to t. And what is the other formula or expression for e raised to t? It is as the limit, as n tends to infinity, the natural number n tends to infinity of a power, and the power is 1 plus t divided by n raised to n. The limit of this, as n tends to infinity, taking values 1, 2, 3 and endlessly, is the same function e raised to t. So, with this definition and some investigations of differentiability, etc., one can show that the exponential function has the property that I have talked about, and therefore, the first order equation is very easily solved. One does not use these expressions for calculating the exponential function, because first of all, in both cases, this dot 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 here means just go on adding and adding endlessly. Similarly, here limit means that you take n equal to 50, but that is not good enough. You have to take n equal to 51, that is not enough. Take n equal to 1000, that may not be enough. So, this is also an endless process here. But there are ways of getting approximate value of e raised to t for any given number t, and your calculator does that. It does not give you the exact value, but it gives you a very good approximation, maybe up to 8 places of decimals or something of that sort. Now, back to the second order differential equation, what shall we do? So, one of the methods again uses the property of the exponential function, which we already made use of, and ask, suppose I have now going back d square plus a1d plus a0 acting on x equal to 0, and I am looking at x, what shall x be? Can it be an exponential function? So, if you can try x of t equal to e raised to t, but you can see that this will not be a solution, or it may not be a solution. Why not? Well, one should try. Of course, the textbooks sort of give you the solution ready made, they don't even let you think. But if I am facing this differential equation for the first time and I am familiar with the exponential function e raised to t, let us say, as the simplest of the exponential functions, then I will say, why not try this? So let us try e raised to t. What will happen? Now this is where one can make use of a simple property of the exponential function, which is just going one step beyond the earlier property. What was the property of the exponential function? The derivative of e raised to t was e raised to t itself, or the derivative of e raised to at was a times e raised to at. That is to say, the differentiation is equivalent to multiplying the function by this coefficient a that multiplies t. All right. The special case, of course, e raised to t I can think of as e raised to 1 into t, that is e raised to at with a equal to 1. All right. So this being the case, and the action of d is simply to multiply by a if the function is e raised to at, or if the function is e raised to t, it is simply to multiply by 1. Now look at the left hand side of the differential equation, d square plus a1d plus a0 acting on x. So what is the action of d acting on x? If the x is e raised to t, just multiply it by 1, that means do nothing. So d, it's as if d was replaced by 1. dx is simply 1 into x if x is equal to e raised to t. What about d square x? Well, if d of e raised to t is e raised to t, d of that is still e raised to t. So once again, it's as if d was replaced by 1. And so I have the following result, that d square plus a1d plus a0 acting on e raised to t, the function is e raised to t, is simply 1 square plus a1 into 1 plus a0 multiplying e raised to t. Now is that equal to 0? That is my question. When will it be 0? It will be 0 only when this expression on the left hand side, this coefficient, is 0, and the coefficient is 1 plus a1 plus a0. So if that is 0, then only e raised to at can be a solution of the differential equation that we are looking for. So e raised to t is not going to work. So let us try the slightly more general exponential function. Now here it is customary in mathematics textbooks to use, instead of a, the letter m, and it's good for us because I am already using the letter a to denote the coefficients. In this case, a0 and a1 are the two coefficients that are involved in the differential equation. Remember, linear differential equation with constant coefficients. So let us try to see whether e raised to mt is a solution of the differential equation, that is whether xt equal to e raised to mt will work. Now what do we have to do? We simply have to act on e raised to mt by this operator, or as one says in mathematics, apply this operator to this function e raised to mt and see what happens. Well, as we saw earlier, derivative of e raised to at is a times e raised to at. So differentiation simply multiplies the function by this coefficient of t. So d of e raised to mt will be m times e raised to t, and so it's as if a1d e raised to mt is simply a1m e raised to mt, that is, replace d by m. So d of e raised to mt is simply replacing d by m times e raised to mt, and if I have m is the coefficient of t, so if I had a1d e raised to mt, then that should be replaced by, or that is equal to, and therefore it is as if this d is replaced by m, so a1 into m e raised to mt. So this rule that when the differentiation operator acts on the exponential function, it's as if d can be replaced by the multiple of t, and that is sometimes referred to as the exponent in the general exponential function, although mt is really the exponent of e. As you know, 10 raised to minus 10 or 10 raised to 20, we refer to what you put at the top as the exponent. So e raised to mt is the exponent, but for our work the coefficient that multiplies t is conveniently thought of as the exponent of the exponential function. So if I go back and try e raised to mt as a solution of d square plus a1d plus a0 equal to 0, the result I will get on the left hand side will be m square plus a1m plus a0 multiplying e raised to mt, and when is that equal to 0, or can that equal to 0? Well, e raised to mt is never 0, as we saw earlier. So this expression in the bracket, if it is 0, then this whole thing will be true, and therefore e raised to mt will be a solution if m satisfies the condition m square plus a1m plus a0 equal to 0. M satisfies this condition. This condition in mathematics text is sometimes known as the indicial equation, meaning it is an equation for the index or the exponent, and the indicial equation is very easily obtained. I have the operator d square plus a1d plus a0. Corresponding to that, I have the indicial expression m square plus a1m plus a0, and I have to solve the problem of finding out a number m such that m square plus a1m plus a0 equals 0, equal to the number 0. On the left hand side here, I have operators only, or I may have an operator acting on a function such as x. Here this is just an ordinary equation in which m is a number to be found out. It is a polynomial expression in m once again. It looks like the polynomial in d, except d is replaced by m, but this is now a polynomial equation involving a number, unknown number m, or a variable m which is just a number, whereas in d square plus a1d plus a0, d was an operator, not a number. It was something that acts on a function to change it into another function. There is a big difference between these two, but from this we easily get this. Now again, the solution of a, what is this equation called? This is a quadratic equation. The solution of a quadratic equation is something which no electrical engineer can afford to forget, and I hope you have not forgotten it. The solution is important, even a simple quadratic equation for an electrical engineer in particular, and somebody who studies systems like this, electromechanical systems, so even for mechanical engineers and chemical engineers and so on, even the simple looking quadratic equation is very important. You may of course remember the formula for the solution, but what is even more important is that there are several cases which have to be considered. The formula is one, but then from that formula, depending on what the numbers a1 and a0 are, you will get different cases. I would like you to go back to your algebra text and have a look very quickly at the 3 cases or 4 cases, depending on whether one of the cases is looked upon or split into 2 cases or not. Remember, these numbers a1 and a0 in our electrical example or electromechanical example are simply some real numbers. They may be positive or negative, but they are real numbers like 5 minus 20 or what have you. They are not complex numbers, they are real numbers, and ultimately they will come from a resistance value being 100 ohms or a EMF constant being such and so on, or x of t itself is a real number because it may be voltage or current or torque or speed at any time t and so on. Now the cases of the quadratic equation solution depend on what is called the discriminant. The discriminant, again, because the letter d, one uses the Greek letter delta, and the discriminant of this in this case is what? You may remember it of course as ax squared plus bx plus c equal to 0. That is the quadratic equation with a coefficient of x squared which is not 1. In that case the discriminant is b squared minus 4ac. This number is called the discriminant of the quadratic equation, and so in this case, because the coefficient of x squared is 1, our discriminant will be a1 square minus 4a0. This is the discriminant of the quadratic equation. And what are the cases to be considered? The cases to be considered are, this discriminant may be equal to 0, it may be positive, that is greater than 0, or it may be negative, that is less than 0. If the discriminant is 0, which means of course that a1 square equal to 4a0, the numbers a1 and a0 are such that this is true, then we get one case. And what does this case correspond to if the discriminant is 0? It corresponds to the case when the quadratic is actually a perfect square of a linear expression, and therefore it has only one root, or 1 0 as it is sometimes called. Or if you wish, you can say that it has two roots, but the two roots coincide. Actually, that way of talking about two roots coinciding, when you studied in school and I studied in school, really did not make any sense, because if two things coincided, then are they two or are they one? But there is a good mathematical reason for using this expression two roots which coincide, rather than saying that it has only one root. So accordingly, then if delta is equal to 0, there is only one root, or if you wish, two coincident roots. So that is one case, the discriminant equals 0. Then there are the two cases, the discriminant is positive and the discriminant is negative. If the discriminant is positive, then there are distinct roots, that is, there are two roots to speak about, and they are both real. So we have two real distinct roots. Whereas if the discriminant is negative, then there are two distinct roots, but they are complex. And there may be this fourth case that I mentioned, that is, this case of complex roots may be split into two cases. One case is when the root is purely imaginary number, and the other case is when the root is complex but not purely imaginary, that is, it has a real part which is not equal to 0, but it also has an imaginary part which is not equal to 0. So in this way there can be four cases of the solution of the quadratic. The roots are two coincident, there is only one root, and in this case the root is real, so there is one real root. Then there are two real distinct roots, then there are two distinct complex roots, but as two sub cases, the two roots may be purely imaginary, or the two roots may be complex with both the real part and imaginary part not equal to 0. Now I will just quickly give you a few examples of all the cases, and some of the cases we will come across later on when we look at our motor control problem, and I can go backwards to construct the quadratic whose roots will be of this kind. So for example, take the quadratic m plus 2 square, which is m square plus 4m plus 4. Now the way I have obtained it, it is m plus 2 square, so it is clear that the root is only one root minus 2, or there are two coincident roots each minus 2, if that is the way you want to look at it. And you can check that the discriminant is 0, delta is equal to 4 square minus 4 into 4, and that is 0. So that is the case of one single root, or it is also then called repeated root, and all these terms, if they are understood well enough, but if they are not, can cause a lot of confusion. Or a root of multiplicity 2, again another expression, or two coincident roots. Then let us look at the situation delta greater than 0, so that there are two real distinct roots, and again I can construct an example, m plus 2 into m plus 3. If I take that and work it out as a product, it will be m square plus 5m plus 6, and because of the way I have obtained it, I know what the roots are. What are the roots? M equal to minus 2 is one root and minus 3 is the other root. Both are real and they are distinct. Minus 2 is not the same as minus 3. What is the discriminant delta here? Delta is 5 square minus 4 times 6, that is 1, which is positive. So discriminant is positive, the roots are real and distinct. Let us take the case of two imaginary roots, and because the coefficients a1, a0 are real, we will see that the imaginary roots will be just the negatives of each other. So how do I construct it? I can construct it like this, say m plus 2j into m minus 2j. Work that out as a product. What is j here? J is the electrical engineer symbol for the complex number which is the positive square root of -1. That is the square root whose argument is pi by 2. In mathematics, one may use the symbol I in place of j, and therefore we have the property j square equal to -1 or I square equal to -1. So m plus 2j into m minus 2j is what? It is m square plus 4, as you can verify. And what is the discriminant there? Delta equal to, the m term is missing, so 0 square minus 4 into 4, and that is equal to -16, and that is less than 0. So the roots are going to be complex, but in this case not just complex, they are purely imaginary. The roots are 2j and -2j, so they are purely imaginary roots. And then we will have the last case, that is the roots are complex but not purely imaginary and therefore also not purely real, and I can construct that also as follows. I will write down m plus 1 plus j into m plus 1 minus j, and if I take that product, then you can find out that it is m square plus 2m plus 2. What is the discriminant here? Delta equal to this coefficient square, so 2 square minus 4 into this coefficient, so 2, so it is -4 less than 0. So it does correspond to the case when the roots are complex. But what are the roots here? The roots are m equal to -1 minus j and -1 plus j. So the roots are complex, distinct, they are different from one another, but they are not purely imaginary. If this -1 was not there, the roots would have been plus j and minus j, as in the earlier case. They would be purely imaginary, but they are not. They are really complex, you can say. Now I will mention here something which we will come across a little later, and in fact quite a bit of it, and namely, when you come across roots of equations like this, which are real numbers or complex numbers, they are shown on what is called the complex plane. So this is something which one should learn, and again one of the most important simple things that an electrical engineer is required to know. A mathematician or a mathematics student may not really plot such things, because for him they are not particularly important, there are so many other things, but for electrical engineers these things are extremely important. So let me look at the various examples that I took, and I will show you how we show it on the complex plane. What is the complex plane also called? It is sometimes called the Argand diagram, named after the French mathematician Argand diagram. So we had the first case of m plus 2 square or m square plus 4m plus 4 equal to 0. So the two roots were -2 and -2. So I will show them on this diagram by putting a cross here, and I will put the two crosses very close to each other, suggesting that they are really the same, and I will put down here -2, or because in general a point here anywhere represents a complex number, I will write this as -2 plus j0. So this is the quadratic, or the roots of the quadratic, or the zeros of the quadratic m square plus 4m plus 4, or the solutions of the equation m square plus 4m plus 4 equal to 0. They are -2, only one solution, or one solution repeated 2 times, or multiplicity 2, or 2 coincident roots. So this was one case. The second case was real and distinct roots. So there I had one root which was -2 and the other root which was -3. So I will show it in a different color. Of course now I have to show it on the same diagram, so I will show it here a little bit on the top as -2, and so there will be another root here as -3. So I will have -2 and -3 as the two real distinct roots of the quadratic m square plus 5m plus 6, or the roots of the equation m square plus 5m plus 6 equal to 0. Two real distinct roots. In this case both are negative. Then we had the third case where we had roots were purely imaginary. So where would they be on this diagram? They would be on the so called imaginary axis, and the two roots were, what did I have them as, plus minus 2j plus minus 2j. So drawing roughly to the same scale, here is 2j and here is minus 2j. So these are the two purely imaginary roots. They are complex, but they are purely imaginary. The real part is 0. As you know, this horizontal axis, so to speak, is called the real axis, and the vertical perpendicular axis is called the imaginary axis. And such a diagram is called the complex plane representation of a, or the representation of a number, complex number in the complex plane. So this is the third case of purely imaginary roots, and now we will have the fourth case where the two roots were complex but distinct, and therefore they were like this. Here was the root minus 1 plus j, and here will be the other root minus 1 minus j. So we have two complex roots which are distinct, but they are not purely imaginary. Of course they are complex, so they are not purely real like minus 2, and in this case they happen to be what are called conjugates of one another. In fact, 2j and minus 2j are also conjugates of one another. Two complex numbers are said to be conjugate when what happens? When they have the same real part, but they have imaginary parts which have opposite signs. So we have complex conjugate roots, and therefore going back to our statement, depending on the value and sign of the discriminant, when delta is equal to 0, the roots are real but repeated, or there is only one real root. When delta is positive, there are two real distinct roots. When delta is negative, there are two complex roots which are conjugates of one another. However, in one special case, the roots may be simply purely imaginary. In the other case, the roots are complex and not purely imaginary. So even as simple a thing as a quadratic then has this variety of situations associated with it, and we will see that this has important consequences in our study. I am looking for a solution of a second order differential equation, and it seems that e raised to mt will be a solution if m is a root of the corresponding quadratic or the indicial equation, in our case m square plus a1m plus a0 equal to 0. This e raised to mt will be a solution of the differential equation, because it is easy to show that if e raised to mt is a solution, then if I multiply it by any number k whatsoever, it will be a solution. That is, if e raised to mt is a solution, 10 times e raised to mt will be a solution, 10 raised to minus 3 times e raised to mt will be a solution, and so on. And so it is not just one solution that we have when we have found this m, but any multiple of it is a solution. So there is an infinite number of solutions that we have found out this way. But that is not all, because this is a quadratic. So in general it will have two distinct roots, and therefore there will be two values of m, and it is traditional to call them m1 and m2. So e raised to m1t will be a solution, that multiplied by any coefficient k1 is also a solution. E raised to m2t is a solution, that multiplied by a coefficient k2, and k2 because it may not be the same as k1, this also is a solution. But one can go one step further. Not only are these two also solutions, but their sum is also a solution of the same differential equation. Now all this is a consequence or is related to the fact that the differential equation that we have is homogeneous, that is, the right hand side is 0 and the left hand side is linear. And I told you that the word linear has some deep meaning associated with it, and we will come to that deep meaning a little later. But you should perhaps try to think about it, that is, why is the differential equation said to be linear? And one of the, this what we have just now looked at is a sort of a hint that e raised to m1t is a solution, then k1 e raised to m1t is also a solution, e raised to m2t is a solution, then k2 times e raised to m2t is also a solution. And when these two are solutions, k1 e raised to mt is a solution, k2 e raised to mt is a solution. Given this, their sum is also a solution. This is connected with the fact or with the statement that the differential equation is linear. And so now what do we have? We have a set of solutions of the second order homogeneous equation. k1 e raised to m1t plus k2 e raised to m2t, where m1 and m2 are the two roots of the quadratic indicial equation, and k1 and k2 are any two arbitrary numbers. For each choice of k1, k2, you will get one solution. So we will get not only an infinite family, but we will get an infinite family which is said to be doubly infinite, in the sense there is a k1 that I can choose as any real number. So one choice, think of real numbers as put in some bag, then there are infinitely many real numbers, I pick one of them, and then I pick another number k2 from the same bag, maybe the same number, maybe a different number. So I have two choices. So that is why it is said to be a doubly infinite set of solutions. Or you can think of k1 and k2 as two parameters of the set of solutions. So for each value of k1, k2, you get one solution. So we get solutions which are parameterized by two numbers k1, k2, and there are two parameters. So parameterized by k1, k2. Now of course, in a given situation I am given actual numbers a1, a0, so I find the roots of the quadratic. So I will get m1 and m2, but what about k1, k2? How do I get these numbers k1 and k2? Because I am not solving just the differential equation as I told you, but there are also what are called initial values, initial conditions, or boundary conditions. In other words, we have an infinite number of solutions, but my actual physical system has only one particular behavior. Say the voltage varies this way, or the speed varies this way, and so on. It does not show infinitely many behaviors at one and the same time. So which one of these is what I am going to find? Now for that I need the initial values or boundary conditions. Now just as for the first order differential equation, it was enough to know what x0 is, the value of the solution at time t equal to 0, because in control theory our action begins at some moment of time which we call 0. What was the system variable x at that moment? If I know that x0, and if x satisfies a first order homogeneous equation, then I know the solution uniquely. This is what we saw earlier. Now we have a second order differential equation, and so I need two initial values, but two initial values of what? X is only one function. It turns out that I need to know the value of x at 0, and I need to know the value of the derivative of x at 0. Not only if x is some position, the position of the particle at time t equal to 0, but then dx is the velocity, I need to know the velocity of the particle at time t equal to 0. So if my differential equation say describes the motion of a particle under the action of no external force, perhaps zero input or free motion, mass spring dashpot system in the beginning, remember that, that is one example. Then I need to know the initial position of the mass and the initial velocity of the mass to determine the position x of t of the mass for any future time t greater than 0. So I need to know these two initial conditions x0 and dx0. Knowing them, I can determine these two parameters k1 and k2 uniquely. Of course all of this really is familiar to you, but I am revising it because we cannot afford to forget it, and because it is going to play a very important part in our analysis. And remember, we are only looking at some simple control systems. We are not really doing anything very complex and sophisticated. This is just a beginning course in control engineering or control system theory. So these are really very simple things. There is much more to be studied. So let us not get stuck here, but then if you do not know this, then there is no point in going further. So given the initial values x0 and dx0, how do I determine the coefficient k1 and k2, or the parameters k1 and k2? In other words, what I am saying is, for the solution I have x of t equal to k1 e raised to m1t plus k2 e raised to m2t. This is x of t. I have found out what m1 and m2 are by solving the quadratic, but I do not know what these two parameters or coefficients k1 and k2 are, and I want to determine them. So I said x0 perhaps will help. So what is x0? Put t equal to 0. What do we get? Exponential of 0 is 1, so I get k1. Exponential of m2 into 0 is exponential 0, it is 1, so I get k1 plus k2. So I get an equation k1 plus k2 equal to x0, and x0 is supposed to be known, then I know k1 plus k2, but there are two of them, not one, so I need one more equation. So I look at the derivative of x. Now what is the derivative of x if x is given by this expression? D of xt will be equal to d of this, and what is d of this? It's m1 times that, so I'll get k1 m1 e raised to m1t, and the second term becomes now derivative k2 m2 e raised to m2t. Now if I evaluate the derivative of x at 0, and I am writing it as dx at 0, then what is it? k1 m1 plus k2 m2. So I have one equation here, k1 plus k2 equals x0, and I have another equation, k1 m1 plus k2 m2 equals dx at 0, the derivative of x at 0. I have two simple equations, linear equations, ordinary simultaneous linear equations for the two unknown coefficients or parameters k1, k2, and in this case I can solve them and get k1 and k2 uniquely, that is, there is only one pair of numbers k1 and k2 which will do the job. K1 will multiply e raised to m1t, k2 will multiply e raised to m2t, and the two values of k1 and k2 can be easily calculated. And I said uniquely because I have assumed without telling you that m1 and m2 are distinct, that is, I have two distinct roots of the quadratic. So it's not just m1 and m2 and that m2 is just equal to m1, but I have made the assumption that m1 and m2 are different, that is, they are really two distinct roots of the quadratic, because if m1 and m2 are really not distinct, that is, they are the same number, then what is the point in writing e raised to m1t and e raised to m2t? They are the same function. I might as well have combined the two functions into one single function. So in other words, we are assuming that the discriminant delta is not equal to 0. So if the discriminant delta is not equal to 0, then if we know the initial conditions x0 and dx0, then we have found out the unique solution of the differential equation. So we have to consider the case when the discriminant is equal to 0. What do we do in that case? Now I hope you recall from your math course that in this case e raised to mt is one solution, where m is the root of the quadratic or two coincident roots, so that's really one root. But there is also one more solution, and what is that solution? It is t e raised to mt. So e raised to mt is a solution, so also t e raised to mt, and because of that, once again I can write x of t, or I can say that the following is also a solution. What function? X of t given by k1 e raised to mt plus k2 into t into e raised to mt. So once again we have two parameters k1 and k2 appearing in the general solution of the differential equation, and once again we have the problem of determining these k1 and k2, and we can determine them in exactly the same way as we did earlier, namely by knowing x0 and dx0, we get two equations for k1 and k2 which can be solved uniquely. And so this is the special case that has to be treated separately of two coincident or repeated or root with multiplicity 2. So as I told you earlier, even the quadratic equation, such a simple thing, when it occurs in the solution of differential equations, when it occurs in the description of systems that we are going to look at, you have to handle these various cases. We have to consider various alternative situations, and there is a big difference between a solution of the kind e raised to m1t plus e raised to m2t with appropriate multipliers, where m1 and m2 are real numbers, and a solution of this kind k1 e raised to mt plus k2 into t into e raised to mt, where there is only one exponent m, and in one of the functions we have a multiplier t. There is a difference, as we will see later on. Of course, what about the other cases that I talked about? When I have simply said m1 and m2 are two roots, I did not ask whether the roots were purely imaginary or they were real or they were complex. I only said that they should be distinct. But for us it will be important to distinguish the cases. M1 and M2 are both real, M1 and M2 are both purely imaginary, or M1 and M2 are both complex with real part not equal to 0 and imaginary part not equal to 0. And that is because how the function x of t, the solution x of t will behave with time, that is what will happen to it as time passes, depends on the nature of the solution, whether it corresponds to the exponent which is purely real or purely imaginary or complex, as we will see later on. So these 4 cases that I talked about, this distinction between the 4 cases and what happens to the solution in each one of the 4 cases, it is very important to know it, although it is very simple. Well, there is actually one more assumption that I have made and I have just gone ahead with it, and some of you perhaps will be a little uncomfortable because I have not stated that assumption. I said that if e raised to mt is a solution, or if I substitute, then m must satisfy a certain condition, and therefore if m satisfies that condition, namely the indicial equation, then e raised to mt will be a solution. So we are led to the quadratic equation, its 2 roots or 1 root, etc., etc. So I have found one set of solutions of the differential equation, but can there be other solutions? I know the exponential function, so I choose e raised to mt, try it, see if it works. It works if m is a root of the indicial equation. Then I multiply it by k1, I get again another solution. I get m2 e raised to m2t, I multiply it, add, so I get the whole family of solutions, k1 e raised to m1t plus k2 e raised to m2t, as we saw earlier, this one here, k1 e raised to m1t plus k2 e raised to m2t. The question is, can there be other solutions other than this? That is, are these the only solutions? The answer to that is yes, but it is not easy to prove that these are the only solutions. So that the 2 parameter family gives you all the solutions of the second order differential equation is a result which is true, but it is not easy to prove it. It requires some good bit of mathematics to prove, but it can be proved, and therefore we have the complete set of solutions of the second order differential equation available to us. We do not have to look for anything more. Secondly, we can also show that knowing the initial values x0 and dx0, we can uniquely determine k1 and k2. So given the initial values, the solution can be found out among that infinite set. We have this infinite set, doubly infinite set of solutions. Which one is actually going to be the case can be found out if we know x0 dx0. So knowing the initial values, the solution can be determined uniquely. So this is the situation for the second order or second degree linear differential equation with constant coefficients, which is homogeneous with 0 input or free system. Even for such a simple thing, the considerations are fairly involved. What happens if the differential equation is of higher order or higher degree? Well, we can expect that there will be more work and there will be more complexity to the problem, and we will have to look at it, because in practice you just do not come across only second order systems, you come across higher order systems, systems of much higher order, and systems which are not described simply by an ordinary L, D, E, W, C, C, and systems which are homogeneous. We have to consider the effect of inputs or forcing functions. So we have to get into a greater depth, as we will do very soon. But as you will realize, this method of finding the solution is really too simple. It is trying to make the exponential function do the job. Fortunately, it does the job all right. In fact, we will see that for higher order differential equations also, the exponential function will do the job. But whenever there is an input present, then this exponential function by itself may not be enough, and so one may have to look at other methods of solving the differential equation, and one of them I mentioned earlier, namely the method that uses the Laplace transformation technique or the Laplace transformation method of solving such differential equations. So to that we will turn next.